Oh, Google got you. Okay, let's get started. Let's see. Homework 4 is due. Wait, homework 4 is due already. Got it. True facts. All right. Homework 5 was released and is due on Monday. We'll have office hours this week. We already talked about this, but your project ideation slides are due tomorrow by the end of the day. And then we'll have our ideation event on, our team formation event on Friday evening. This is a great, really what this event is about, you guys figuring out if you have any ideas in common with anybody else. That's an important aspect. And then trying to vet through that idea for the first time. So I'll be there, Matt will be there, and one of the IAs or GSIs will be there. So you can talk to them and be like, is this even plausible for 473 project or 373 project? And we'll kind of walk through what would that look like and give you guys some advice on how you'd actually achieve that. So that's the goal of the event. Hopefully you'll come out with partners or at least have a solid idea of who will be on your team. Any questions? Okay. I'm actually going to be traveling next week. I had a conference travel planned anyways later in the week, and I have a small family emergency, so I will not be in town. But Matt Smith will give lectures. He's definitely can do it on Wednesday, probably do Monday, or I'll have another professor come in. So look for details on that. At minimum, I'll go and post lecture recordings beforehand. So if if nobody's there on Monday, at least you'll have a lecture recording to look at for that period of time. Now, because I'm not going to be there, that means everybody gets free class participation points, because if I'm not there, you guys can have a free one. So if I'm not going to participate, you guys can get a free pass on 1 year points. So there you go. All right. So today we'll do a very quick review on timers. We'll get through virtual timers probably, and we'll start on communication buses. So before we get going, is there any questions? Yeah.
No office hours this week either.
No, office hours this week, Thursday.
Next week.
Yeah, no office hours next week. I'll get one of the IAs to help you with office hours. That's a good idea. Okay. All right, so input capture timers. So these are the timers that we'll use to capture external events. That's typically what they're used for, although they're flexible. So the big ideas here, just review, you have some clock that comes in, you can pre-scale it down to whatever, not whatever, but a lower frequency. And then you are going to say, let this timer run for a period of time. So you're going to start at 0, you're going to count up, and then some event is going to come by. It's going to cause this to capture the value that's in that timer and hold it here, and then send off an interrupt. So it's really good for trying to figure out what's the duration of time between button pushes. You think about most of your smart devices, if you hold down the power button for like 3 seconds, it will reset, right? So how do they keep track of that? So when they see the button's been depressed, right, they start a timer, and then they're just basically waiting until it expires or goes past a certain amount, and then they're going to go trigger that hard reset. There's lots of ways you would use that, but that's a common way. Any questions? How would you, what would be an example of how you would use it in embedded systems, other than my example? Yeah.
Encoder.
A what?
Encoder for rotations.
Yeah, you could do that. How would you do that?
The encoder would stick signals into it would capture it in the encoder's time, I guess.
Okay, so kind of like the homework assignment where you had the wind meter that went around. You could do it that way. Yeah, I would think like a typical, well, depends on what type of encoder. You'll see ones that are like little discs with that you shine light through basically, and then you can actually read off the absolute value or the relative value. But yeah, you could use encoders or timers to help with that. All right. Oh, and of course you can set up, the typical thing is you're going to set up an interrupt service routine to handle that, although there could be any other ways. You can still go and poll for this particular thing. That value is going to stay there for a long period of time, depends how you set it up. So it doesn't have to be an interrupt service routine that is triggered off of it, but that is typically how it would work. A good way to get asynchronous events. The other mechanism is the capture, the compare timer. So this is measuring the passage of time, usually from an internal point of view. You're not necessarily looking for an external event. So we talked a lot about setting up PWM. So again, you have some clocks coming in. You can scale that down to some value that you like to measure the passage of some time. Then you say, okay, you're going to load your target value when you want an event to occur into the capture compare register. You have to configure the timer to be in compare mode, but the same register for capture and compare. So you put some value in there. When the timer equals that value, then an interrupt goes off. Any questions? Okay, great. And then just as a reminder, you will have, this is a typical kind of block diagram for the STM32s you have. We've gone through all those blocks, so they're just in a different space, different shape. But the key idea here is that you oftentimes have multiple capture compare timer or registers for one timer, which means you can do multiple events at a time. You don't have to have just one timer going off per event. And that just lets you have more and more events that you can keep track of. The most plausible usage here is, say you had 4 motors, 4 servos on some robot chassis for some arm, or maybe you're trying to drive a 4-wheeled vehicle, and now you can control the speed of each one of those independently by setting up different duty cycles with the capture compare timers and registers, only using one timer. So that's a way to kind of simplify how much hardware you have to use. All right. Anybody have any questions on timers in general? All right, onward and upward. So kind of getting us prepared for thinking about virtual timers and why they're useful. Why don't you guys work together? Just it's not a worksheet question, but what is the maximum amount of time that you can count? What's the maximum period for 16-bit, 32-bit, and 64-bit timers? So work together, and we'll check in after a couple minutes. What's the idea?
The idea is that it's like the highest number of times that you can count, and that's just the time period, so we convert that to like or something. And then we count 40.
Yeah.
Like 1 per. Is that in the range or should it be accurate?
Definitely in the range. You've gone for partial credit so far.
Okay.
I think the question is asking like with a 60-bit timer so far, just interval of time out and count if that's your clock.
Okay. So would we be incrementing every time? Maybe 164. Based on something else.
How? So you had a timer that we talked about before, and you don't have any preset levels. That's the clock going into your timer. What's the answer to your question? The timer's going to tick every time.
Yeah.
Okay. Yeah, if you're on it.
So now we're calculating. One over 10 to the 8 is megahertz or 0.01. Okay, why not?
Then divide by 24.
I had 2 to 64.
Divide by 7.
It's not working out though. I got that number at some point. I got that number at 1
How many years?
I think it's
That's 8 years. Times 2 to the 64. 2 to 64
times 1 over. And that's in centimeters and
2 to the 64 divided by.
okay, so the same number I have.
No, I think. I don't know. Oh, I see again. I saw your idea on the thing. Okay, I was dividing by 60 divided by 60 is
Yeah, that's what I'm doing.
and then dividing by what am I in? I'm in hours, so that's like
Yeah,
24.
that's the scaling.
Okay, I guess you're right.
This number is that in milliseconds?
The 64 bit. I mean,
What'd you get?
like 5,000 years, almost 6,000 years. It seems like 64, 2 to 64 is just an absurdly large number.
It is a large number, you're right.
Much larger than 2 to the 60 is.
But megahertz, 100 megahertz, does that convert to nanoseconds? I feel like it's a little less.
Oh, I wait.
Oh, go on. All right, so how we go about solving this problem? Anybody want to propose a solution? I heard correct solutions out there. How about some other people? I talk to you a lot. You're great, but I'm teasing.
Didn't really know how to start. I just went with well, if you have a 16-bit timer,
Yeah.
you can just max it out.
Yep.
2 to the 16. And I don't know how much is that in seconds.
Well, how? Okay, but how? Okay, so you got a timer that's going to count up that many what? What's it going to be counting? At least clock edges, right? And so we got a 1 megahertz or 100 megahertz clock. How do we turn this into time? 10 time. Yeah, okay, that's about right. So basically, I didn't follow all that because I couldn't hear it quite well, but you turn this megahertz into period, and you multiply that by 2 to the 16th. Okay? What did people get for answers? Yeah.
64 bits like 5,800 years. If you go for the 0 and go over the.
All right, how about 16 bits? Let's start with 16 bits. That's true, yeah. 11.2 seconds. That's what I got for 16 bits. Did I do it wrong?
Oh, no, wait. That was for a different video. Okay. So just looking at
All right, who got this answer? Anybody get this answer? All right, we'll vote by majority. That's also how we correct your exams. Sometimes we're like, oh, wait, we messed that up, okay.
Could you change timer mode to be like count up and then count down and double that?
You could, yep. Yep. All right, how about 32 bits? What'd you guys get? 32 bits.
42.95 seconds.
Yep, there you go. And then we already kind of called it out, but 64 would be 5,845 years.
Wow.
The power of log here, basically, right? So I guess the question might be, why don't, what's the question? You only really get 32-bit timers, or 16-bit timers on your MCU, right? Because counting out this far, probably 64 bits, probably not that useful. And your core clock just isn't that fast. If you're maybe going, have a couple gigahertz clock, then maybe it's more useful, but just going that far in time is just not that useful. 32-bit timer is actually pretty useful. And if you want to take your 100 megahertz and use it for something like, 65 milliseconds isn't that useful in itself for human scale things. So typically that's why you have the prescaler to scale it down. So now you can have something that's in the human range without requiring a larger timer or ganging 16-bit timers together or making virtual timers. Okay. So we'll talk about virtual timers. We did a little bit of intro into this. What did we talk about? We went over these slides. Basically, we talked about the fact that you can go through and you could create a timer, and if you start keeping track of how many events you have on your queue, if you made a queue of events, and then you could set a timer to go to your next available, or the next event that was about to go off, you can set a timer for that. When that happens, you go do something, and then you just take off that value of everything else on the queue. So we'll walk through this in a little bit more example, a little bit more detail. We just talked about that one. Okay, so in the construction of virtual timers, you have a program, you have your ISR that does something, and then you have some hardware timer. Okay, so in this instantiation, we're going to have 4 programs, and a hardware timer, and so each one of these programs is going to do something like set up a timer that goes off at, in this example, time 3, time 5. There is this idea in virtual timers of delta timers, that things that repeat. They'll keep going on and on and on after some delta period of time. And then we have this virtual timer, a queue of events that need to happen, and you have your hardware timer. So you get your queue and your timer, and then what happens is you're going to go and load from all the different subprograms or tasks that need to be done. You're going to load in and create a list of times you need to keep track of, and then when your interrupt goes off, you're going to have your your ISR that's going to go and do something. We'll talk about what that is in a second. Okay, and in this event queue or in this ISR, you're going to be controlling the hardware timer to, to insert new events or to reset to the new time that you need to look at. Okay, so let's go through an example, and those are the examples of the event handlers that you would do. You would say, here's your ISR. When some program occurs, when some timer goes off, then you're going to go do some task with that. So that's just the construction of the problem. Let's look through how this works. Okay, so you have, you're starting to build your event queue. So say program 1 needs a timer that goes off in 3 units of time. These are arbitrarily small. Nobody will go after 3 clock cycles. This makes sense, but for this example, say you're going to go off 3 units of time. Then you go to your next program. So you're building your queue. You're going to say, oh, in 5 units of time, I need another timer that goes off. Program 2 wants one that goes into 2 units. The challenge here is you got to go and resort, because you always want, this is kind of looks like a double linked list, where you always want this sorted so that the soonest events happen first. Okay? So you go through your sort, add another time event. In this particular one we're going to talk about, the modes are either it happens one time or it's repeating. It's the delta mode. And then you have your last one. And again, here you're going to have to resort because 4 happens before 7 or 5. Okay. Anybody have questions about the construction of the problem?
The timer is not going off right now because then you'd be using those clock cycles to actually add the
Correct. So one thing that's confusing here is that meshes make the timer times much larger, but we're going to assume that we'll just call these hours. That makes things, or at least minutes, that makes things more tangible. So one of the things is you're going through and sorting this list and building this queue. It does take clock cycles. And so this is one reason why virtual timers are not inherently as precise as hardware timers, because there's this overhead. And it's very hard to calculate beforehand how many clock cycles you're going to use to make that precise.
For delta, I'll just mean it just keeps repeating itself.
Yeah.
Delta is where it resets to.
Correct.
It reaches the 0.
Yep. Yep. Okay. So we're going to start off here. So we have a list of alarms that need to go off in order. And so what you would do is you would go and have your hardware timer set to the next increment that's supposed to go off. So in this case, in 2 minutes, the timer is going to go off. So we're going to set the timer for 2 minutes. Why do we choose that? Because that is the time for the next event. Okay. So here, the timer goes off. We're going to decrement 1 minute, and 0 minute, and that triggers your interrupt service routine. Then you have to go do something. Okay. So what do? You enter your ISR. You figure out what was the source of your event that went off. Right. It could have been anything in your queue, but you have to go figure out. Okay, it was this particular thing in program 2 wanted to go off, and now you have to go do some tasks. So figure out what was supposed to be done. This is not in Delta. Is this Delta mode? Yes, it is Delta mode. So you got to go and remove it from the head of your queue because it's not the thing that's going to go off next. Then you're going to go update the times, insert new event. In this particular case, is a Delta timer, so it is counting as a new event. And so you're going to go put that back in the queue. It is kind of arbitrary whether you decided to put it here or here, right? Both of those would be fine. And then you're going to set a new time. Oh, and I forgot one important part here. I should have said this more clearly. You need to update the times of everything. So let's go back here. So this is when the ISR just went off. You removed the head, and now this was supposed to happen 3 minutes from when you started the program, but 2 minutes have gone by. So you need to go and update everything in the queue. Right, so it's supposed to go off in 3 minutes. However, 2 minutes have already passed. So now this is 1, 2, 3, 5. Now you go insert any new events. So the new event could come because a program or a task wants to add something. In this particular case, it was already predefined. It was a Delta time or something that keeps repeating. So that's going to go back into your queue. All right, so you've gone through, you've inserted any new events if they occur, and then you set a new time. And what's the time we're going to set? 1, exactly. So because that's the next event in your queue. You get 1. And then you're going to go start up your timer again. So all that computation is not, again, just not counted for when you're doing your Delta or when you're doing your virtual timers. So you'd want these timers to be long periods of passage of time or something that's not precise. You could do these for even, you just have to figure out what's the engineering trade-off you want to make. So considering how fast your microcontroller runs, you could probably have this being still controlling a motor if you wanted to, because being off by a few cycles on a PWM is not that big a deal, but if you really needed precise speed, it wouldn't make sense. So it just depends on what the engineering trade-off is, how many timers you have available to you, whether it needs to be super precise or not. All right, so we're going to start our timer. We're going to decrement. We go from 0 or 1 down to 0. Timer goes off, expires. So what we're going to do, we're going to go and remove, figure out the source, go do the task for whatever source that was. We're going to remove it from the head. This time we're not going to add it back in. It's a one-shot event. It's only going to happen once, so we just remove it from the head, and we're going to go restore all the value, or update all the time. So that was 1 here. This is 2, 2, 3, 3, or 3, 5, I mean. So here we're just going to remove that. We updated the times. There are no new events that are coming in, and we set the new time. And here the new time is going to be 1 because that's how long it takes for this until this event is up. Any questions? You may need to do multiple loops or multiple passes for multiple events. Okay. So, the previous example assumes that scheduling all events happen when the timers are first sent. So if you need a schedule event when the timer's already expired, so say you come into the middle of some event, right? The timer's going off, and now a new event has been added to the queue, so we can look at that case. So a new event has occurred. You need to essentially run, this would be a case where you'd want to run like a software ISR or something, force that ISR to run. There's other ways to do this as well, but that would be a reasonable way. You need to instantiate this in the next queue. How the clock's been running for some time. So you go through and subtract the difference. So basically you do the event that we had before, which is you have to stop the clock, you add this event into the queue, and then you need to decrement, because you stopped the clock in the middle of your timing event, you need to decrement the time that's passed from all the other events that have already occurred. So these would get decremented. So in this particular case, 2 seconds had passed or 2 minutes had passed. So we're going to decrement those and then add this timer into that queue and go forward. So how confused are you about virtual timers? Yeah?
So for this specific example, we had the clock running already before
Yep.
any new event got added.
Right, so maybe you could have a long timer, like that goes off in an hour, and your program wants to go and add, 1 minute timer. You don't want to wait for an hour before you get the chance to update the event queue. So in that case, you could just go put your new task on a queue of list of things that need to be added, call your ISR will stop, go look if anything's expired, nothing expired, it's going to go update all the timers. Then you're going to go and look for a new event and add that new event in there. So you have to manually do it. The ISR is not going to go and just check the queue on its own. Yeah.
So does the timer not count while doing the overhead of like taking the timer out, doing whatever it needs to do, putting it back, resorting it?
In the simplest case, it doesn't do that. I mean, you're right. It doesn't. The timer's not going in that case.
So in that sense, then a timed event that's very far along the queue, if the timer on that is like 10, then would it be possible that event would be delayed because of all the overhead?
Yes, absolutely. Well, first, because there are no right answers in embedded systems, I say, does it matter? Right? If you're trying to keep track of when somebody should wake up in the morning, right? Do you actually care if you're a few microseconds off? Not that important. And if you have really time critical things, then you'd have to go through and you maybe use a hardware timer for those time things. There are more advanced virtual timers. You could have ones that have like a constant delay associated with them, or even you could have another timer that's timing how long it should take to do all the updating, and then there's a fixed amount of time. Sorry, you basically say, run a timer, I'm gonna do this for so many microseconds. You assume that you can get your whole queue sorted and everything set up, and then you take that off your overhead. But it's inherently going to be less accurate than a hardware timer. I see you're all super excited about virtual timers. Fantastic. You will see them again in 473 if you get there. Some of you will probably end up needing to use something like this in your project. All right. So we're going to go on to the exciting world of serial buses, if nobody else has any questions. Oops, no. Let's see, where did I put them? Yeah, my desktop's got messed up. Okay, so this is going to be like a 4-lecture series. Instead of having like ones that evenly fit into like a whole day's lecture, there's going to be these 4 modules. So first we're going to talk about serial buses in general, their properties, trade-offs, when you would use them versus parallel buses. And then we're going to talk about 3 specific protocols, UART, so Universal Asynchronous Receiver Transceivers, SPI, Serial Peripheral Interfaces, and I2C, or we often call it just I2C. Nobody calls it the intra-integrated circuit. I don't know, nobody's ever called it that. But that's, we just call it I2C. And so the reason we're teaching these is these are the most common ones for embedded systems. You can find embedded systems that have USB as well. USB is you could think of it as a modification of some of these. It's just that the complexity is so high that you typically don't want to deal with USB directly. Usually you get a chip in between that will do USB for you, and you talk to that chip over SPI or I2C or UART or something. Anyway, so we'll start off with serial buses, architectures, and then go on for the rest. All right, for those of you who get real excited or would just want more description, the reference manual provides, a relatively good description of how UART, SPI, and I2C work. I mean, it does assume that you have some knowledge about it, but at this point, you guys are at the point where you can probably read the manual, not enjoying it, but you can probably read the manual to actually gain enough information about how to use the peripherals. That plus a little Googling will probably work. So that's where you'd find it. For those who want a little bit more description, the embedded systems for ARM Cortex and microcontrollers, make sure it's the 3rd edition, has a good chapter on serial communication at a bit of a higher level. All right, so thus far we've talked about bus structures on chip. So the APB bus and the AH bus, the high performance bus and the peripheral bus. These are all buses that are in silicon, and those have a bunch of different, because of the nature of it being in silicon, you can do things that are just not practical from board to board. So these 3 protocols we're talking about are really designed to go from chip to chip on a PCB. You find buses all the time. So this is an example of a motherboard. So PCI, slots, and all those things. These are, parallel buses. The example of parallel buses. You get the north bridge for your Intel processors and the south bridge. So memory and videos. Well, all the same things are going to be true for these. The complexity is just not worth teaching in a sense. We're typically thinking about some small microcontroller talking to some other chip. And so these are the buses that we'll typically be thinking about. And when you and your projects are trying to get Wi-Fi or Bluetooth or Zigbee working, these are the sorts of parallel or protocols we're thinking of. So there's a few things to consider. So wiring is going to be serial versus parallel. So parallel is great. You can get lots of data through it. So you're going to have multiple wires in parallel. But the challenge there is that you have to have the pins for it. So you think about on chip, it was pretty easy to have as many wires as you want. Those wires are part of the chip. They go above the logic gates, and it's very easy to have. You want 32-bit parallel wires, that's fine. On an IC, the challenge here is you just don't have that many pins. There's no way to put a 32-bit bus on this thing if you want to talk to something else. Why is it that it's hard to have a lot of pins on a IC? Yeah. Would make the chip. It would make the chip huge, you're right, and we're usually trying to optimize for size. What are some other reasons why we don't have a lot of pins on ICs? You could, yeah. Yeah, you certainly, especially not maybe on the microcontrollers you guys are using, but on Intel chips, they still have, or like processors, heat is a real problem. What are some other challenges, yeah?
Really noisy.
Yeah, they are pretty noisy. Yep, they are pretty noisy, especially if you try to cram them together. But why? Okay. Another thing to think about is, remember when I showed you guys there was the chips they dissolved with acid and you can actually see the bond wires going into them? There's just not that much physical space to put wires onto a chip. So say you have a millimeter by millimeter chip, there's only a finite, even if you use the entire surface of it, there's only so many wires you're going to get in and out of that thing. So this is the I/O constraint problem of most ICs, is that you can send as much data back and forth inside the chip as you want, you just can't get the data out fast enough. So we had to invent some protocols that will allow us to get more data on and off the chip, but sending data across the chip is very easy. Does that make sense? So it's these kind of practical engineering solutions that are causing challenges. So some dimensionality in the sense of factors to consider. So we have serial versus parallel. Speed, are you going to send, so serial, you're going to be sending bits at a time, not necessarily bytes or words. So have this inherent speed cost. We're going to talk about timing methodologies, whether you have to be synchronized with the receiver or with the external device, or it can be asynchronous. And all the bus stuff you've seen so far has been assumed to be synchronous, which means there's a clock between them, which counts for some overhead, but can be faster. Another thing is how many different destinations and sources are there? So when we talked about the APB bus controller, right, it was one bus controller that would talk to all the peripherals. So it was like essentially one master and a number of different peripherals. But that doesn't have to be the only topology. You could have one-to-one. You could have as many masters and as many slaves as you want. Whatever the topology, there's different protocols for different modalities. We talked about arbitration a little bit when we talked a bit about the APB bus. But the way it did arbitration is that it had a different control path. Remember, the data path back from the peripherals to the controller was all individual data paths. So there was very little need to have arbitration to select which one it was, because they all had a data path that would come back. They did have an addressing scheme, so you'd say, I want to send an address to a particular device. But there's different ways to do that. So protocols, how's the data formatted, and is there redundancy built into that? So for the APB bus, it's not that noisy inside a chip. Like it is, but it's not that bad. Outside the chip, it can be super bad. So you might want to have some error correction built into your data formats to ensure that the data actually makes it there. So parallel topologies, generally it's some amount of bits, whatever how many bits it is, and just directly wires connecting the transmitter and the receiver. Good for high-speed throughput. Talking about CPUs, talking to memory, that's great, but more expensive in terms of pins, more wires, lots of requirements. And so here are some typical protocols. So SPI, we talked about that, compact flash, different protocols. And this is what you see here. These are examples of buses that you would see on a PCB. Remember, these are lots of wires and lines. You have challenges because they actually want to, you can't see here, but these are individual buses right next to each other, and they'll talk to each other, crosstalk, which means a signal going along one wire will actually jump over and then be imposed on the other wire. And there's lots of engineering efforts to go ensure that you can actually get the data rates out of here while still without having lots of poor performance. Nope. Yep. And just to be clear, so here's an example, parallel bus. So you should be able to play with all these different things from the lecture slides. Some of them, you'll find that like when you copy the URL, there might, PowerPoint sometimes add a space in there when you convert to PDF, but the link itself should work, or just look for that missing space. Anyways, in this example, you have a counter that's counting up. You have a receiver here that takes binary and displays it into decimal. And you can see that each clock cycle, we have this clock going up, so you have the clock down here. In each clock cycle, the value from this register is being clocked into this register over here. So very similar to how your APB bus worked. Ooh. Man, was it this way? Yeah. All right, any questions so far on parallel buses? Yeah.
So why would you want to have a parallel bus where you could just pass that first 8-bit register straight to the receiver?
Why would I want a bus? Well, okay, so I think you might be thinking like back 370 style. Look, I had a bunch of registers over here, I had another bunch of registers over here, and your 5-stage pipeline. Why do I need this bus? Why do we even call it a bus structure? Is that essentially your question? Okay. Great question. Fantastic. These things are typically not close to each other. So even on chip, they're far enough away that you would actually have to think about from electromagnetics point, if you're trying to go fast, there's waves on top of here. So you have to start thinking about this as a structure of bus that's sending data from one place to another place. So there's some EM effects. And you have to start thinking about synchronizing these two, so you need this clock element. When you get off chip, it becomes even a larger problem. You can't just, I mean, in the simplest form, this is what it looks like, but there's a lot of extra overhead that goes into making sure that you can go really fast. Does that answer your question? Ask me your question again.
So I guess what I'm just confused about is why don't the bus is literally just like the lines in between the transmitter and receiver.
Correct?
Okay. I thought the bus was the registers.
So that's a good question. The bus is the lines. The bus is the data format between them. So essentially, imagine that one manufacturer is doing this, and the other manufacturer is doing this, and you have to agree so that people can put your parts down and they'll actually be interoperable. So we build specs around what buses are, but you're right. The thing, if you're going to look at it, you'd be like, the bus is wires on a PCB. How is that complicated? Well, it's the agreement between the two manufacturers that is the thing that instantiates a bus, the wires and the protocol around it.
I guess if the wires like on the board, for example, they're so close together, just to save space and everything, how do you, I guess, stop like one wire affecting the other?
It is a big challenge. So from a 373 point of view, you're probably going to go slow enough that it doesn't matter. So if you're at DC or close to DC or in 100 kilohertz, it doesn't matter. The rule of thumb is, going in the future, if the wavelength of the signal you're doing, you just from the speed of light, is a tenth of the distance, the distance you're trying to transmit data is a tenth of a wavelength, you have to start worrying about RF effects. And that means like impedance matching. Basically, it means if you have a long data line, PCB line, and you're trying to go fast, you should know when to call the RF or analog engineers. Basically, that's what should happen. And if it's about a tenth of the wavelength, then the distance is about a tenth of your wavelength, especially your wavelength in the material, because the dielectric constant of PCBs is usually around 4.7 or so. So you have to scale the factor a little bit. Then you should start worrying, if that makes sense. But typically, you go slow enough, it's going to be just fine. Okay, I don't know if I'm answering any of your questions today. Maybe I'll get there one day. Okay. Nope, this way. Okay. The alternative to parallel buses is serial buses. Again, serial bus could be just one wire. We'll get into all the caveats about one wire, but it could just be one wire. Typically, these things are going to be slower, but you don't have as many pins you have to use. So this is serial protocols are the preferred method for talking one chip talks to another chip. You do need to, there's two different modalities. There's asynchronous and synchronous. Typically, you need some way to synchronize the transmitter to the receiver or vice versa. And so we're just talking about there's been one thing that sends data to the other one. A lot of these protocols also involve round trip, right? So you're going to send data from one person to another. It's going to send data back to you. We're just thinking about in the abstract one direction right now. So you probably need some way to synchronize that. Typically, you're going to add a clock, another wire to send the timing information, just like you would with a parallel bus. However, there are some protocols that are asynchronous, where they recover the timing of when those bits should be sampled from the waveform itself, meaning that there might be some timing bits that are sent beforehand to help you, basically, you oversample the waveform and say, the timing is, there's an edge coming every so often, and then you figure out the phase and when you should actually be sampling. So you could have synchronous or asynchronous. That defines if you need to have a clock or not. Good for, and inexpensive from a connection and terminal point of view. Also, it's good for long distances. One of the challenges for parallel buses is literally getting wires that are very long. There's a practical challenge of making a cable that, say, 300 feet with 32 parallel conductors in it. There's a practical challenge, but also there's electromagnetic challenges. Is that the longer the wires are running next to each other, the more energy per cycle is induced in another cycle and another thing. So you imagine there could be some capacitive coupling, some inductive coupling. So typically, parallel buses need to be shorter. There are probably ways around that than serial interfaces. And so examples we'll talk about that we're not going to talk about necessarily in here are going to be like RS-232, Ethernet, I2C we will talk about. Even IR, I don't know what IRDA stands for, but it's basically your TV remotes. This is all considered to be a serial protocol. That's how they work. Your STM32s already have hardware built in to emulate that protocol, so it's a really well-known protocol. It just happens to be that the signaling format is light rather than a voltage on a wire. All right, and then let me turn this one off. In this example, how does this work? Let's see. Basic shift registers, and we're going to clock in data every single time, and then we're going to go and, oh, here we go. We'll go and load some values. So you had, I mean, this is, in the simplest form, there's a shift register that's going to take some amount of parallel data, turn it into serial data, and then you're going to turn it back. So here, if you knew how many clock cycles you're expecting, you know when to sample this data out. What's that? Yeah. Yes, you're supposed to false. Damn. I'm really good at, computers are really good, I promise you. All right. All right, we're back to Falstad. The typical way you think about this is that there's some standard shift register. You're going to be putting data into your shift register. It gets shifted out, and then you can pull it back out. I mean, there's no requirement that you would have to use a shift register. It's just like the most logical methodology for sending serial data out. So let's see. There we go. So here we're loading the data out. It's being held here. You can see the bits are being pushed across this line. And now you can see the bits are forming up here. And you'd have to know when. You have to have some methodology for when the full word is there. Because if you waited too long, then the bits will all just pass through. It's all getting passed in with zeros here. But so if you knew the timing, you could pull those bits out. So inherently, all the serial buses have something that looks like a shift register to take the world of your microcontrollers, which are parallel-based, get the data in and out the small pipe, which is the GPIO pins, the wires, bond wires that come through. You don't have many, so you're going to use serial port to push them out, grab that data, and turn it back into something that's parallel for the other microcontroller or whatever other device you have. How are we doing? Okay. So other things to consider. You have different encoding modalities. So with parallel, it seems to be fairly straightforward that you would just do, you could do lowest LSB or MSB reversed or forward, doesn't really matter. There's not that many encoding schemes, but there can be a bunch of different encoding schemes for serial, and we'll talk about a bunch of them. But basically part of this is what is the encoding scheme that you need to recover, and we'll find that, oh, is that the test? Fantastic. That's going to be. Fantastic. Modern technologies is helping us out. Oh, good. Now we know who's on Sprint versus AT&T.
You won't know when the bombs start dropping. They'll already be on the ground.
All right. No. What carrier do you have? T-Mobile. Okay. We talked about encoding. As things, what is encoding? You just have to understand the impact of encoding. So whether you have address bits or data bits, all these things will affect your overall transfer speed. Data rates, parallel is generally going to be inherently faster than serial. We talked about the cost of pins and modularity. We'll talk more about error correction in different ways, but I think the key takeaway is that anything on the board, you will see if we get you an oscilloscope and you look at your embedded system projects, there is noise everywhere. And so any of your serial protocols, you should not inherently rely on them to be sending data accurately. So whenever you do your projects, sending in at least a checksum, but also just like a counter, like a simple counter that says, I send a packet of data and then a little counter afterwards, and you can count up to see if you've actually gotten all the data you sent. Like you think it's simple, but some robust measurement of just making sure that all the data got through. And Ethernet we use, or Ethernet or TCP/IP, there's always these packet counters that help you keep track of if the packets actually made it there. So anyways, I encourage you to use those sorts of things. So speed, serial is particularly lower, but it's cheap in a sense. So here RS-232, which is the predecessor to UART, you're talking kilobits to 20 kilobits per second, copper, usually over copper wire. Medium speeds, I2C, optical IR, you can be in the tens to hundreds of kilobits per second. And with different ranges, of course, IR has an inherent limitation in range. And then for high-speed things, USB is actually getting much faster now, but you're in the 1 megabit per second, 60 megabit per second. That and Ethernet can be much faster. I guess one question I have for you guys: these are the stated specs. How close what's your intuition of how close you can get to these stated specs from the manufacturer? If they say you can get 2 megabits or 1.5 megabits per second over USB, how likely is it you're actually going to get that? What are some factors you think would limit your actual USB speed? Yeah. You could have physical damage to your thing that would limit it. It's a little less likely, but what are some other factors that might impact?
Power supply.
Yeah, you could have. There was a while actually that, especially on Intel platforms, where you would plug in your USB 3 device and your Wi-Fi would stop because the bandwidths were about the same and it would corrupt the Wi-Fi chip. Yeah. That's true. Even just because you have the spec means your device could be underpowered. You certainly see that a lot of time with cheap electronics where it says it's USB 3, but you're like, just not getting the speed. Any other ideas of why you wouldn't? Yeah, so kind of back to the wiring connection problem. You also find that when they state these speeds, that is like bits of information going past under like the most ideal situations. But it doesn't count for any packet overhead. We'll talk about that. So you're already reduced because you have to have the protocol itself is going to induce some overhead. And also, I think somebody said about your device isn't fast enough, just inherently, it's unlikely that your protocol is going to be able to pack this pipeline or this data path full of packets every single time, right? There's always some inherent delay. So even though you think you're going to get close to that, always overspec your serial communication. In some ways on your projects, you don't get a lot of overhead, you don't get a lot of flexibility, but if you're going to use I2C, don't try and expect it to be able to get the maximum data transfer just because that's what the protocol or spec says. That's like under the most ideal cases with all the overhead. Yeah?
Why do they tell us we can't fly?
What's that?
Why do they tell us these specs aren't in our case that? Why wouldn't you just tell them like their average? Market.
Yeah. Exactly. You want USB 3 because it's faster. I promise you want that. Yeah, it's just marketing. And it's funny because a lot of these things you're not marketing to you. It's like some manufacturers marketing to Intel or something, like, but it's all this funny. It's funny business in some ways. Yeah, keeping us engineers employed. So you can't live without them, I suppose. All right. Yeah.
I have a kind of dumb question about serial. Like when we say that it's like 10, 10, 10, is there actually like a part of the wire that's high while another part of the wire is low?
Yeah.
Or is it just happening really fast?
I see what your question is. You're saying, I don't know. Well, nobody's drawing anything in this room today. You're saying, is it possible you have say we had a really long line, is it possible that you could have the first part of this line could be high while the lowest part is still, or the farthest part is still low? Oh, they are over there. It's a good thing you're here. Fantastic. Basically, long transmission line, TX. You guys can't see what? X. And you're saying you put a pulse here, but is this thing actually gonna change in time? What's everybody's intuition say? What would be the factor? Okay, if it's long enough, okay.
I was thinking you just send, so like let's say we're sending 101.
Yeah.
It would pulse one high for like, I don't know, a second, and then low.
Okay, so the alternative modality here is that you got your oh, you guys can't see that. All right. TX, I never used these things before. TX, RX. And you're saying, so this could be a 1 here, and there's a 0 over here, 0, 0. And you might say the alternative method would be we're going to transmit 1, 0, 0. And it could be that the first, there's a 0, there's a 0, 0, and then there's a 1, right? So that at any time you look at it, the whole line would be a single value, and in this modality, part of the line is a different modality. Which one do you think it is? Let's see. At any one time shot, the entire line is a single value. Raise your hand for that one? Okay, and then at any time shot, you might see a 1 or part of the line would have a 1 or a 0 on it. Who believes that one? Oh, I like you.
I guess both would be possible, right? Because it depends on how long the...
And what's another implication of long? What's the inverse of long? That's not what I meant. Fast. So if your signals are very fast, this is what happens. So this modality is what you'll probably see everywhere in this class, no problem. You will, even if you get up to a megahertz, the distance, the change in the voltage happens almost instantaneously. You won't be able to see that. However, if you go to very fast buses, gigahertz, multiple gigahertz, then you literally do see this. You will see that parts of the waveform will be here. And actually, those buses act much more like radio signals and propagating radio waves. They just happen to be confined on a bus structure. And so as you go fast, you have to start worrying about all these extra effects. Yeah.
Would you be worried about, I guess, like that 0 spilling over to that 1 if you're sending on everything at once?
Yeah, and what you see sometimes is for high-speed buses, you see what they call like an eye diagram. Let me see if I remember how to draw them. Right, and they're trying to say like, look, you either want to measure a 0 or you want to measure a 1. How fast can I push these together while they're still distinguishable? And what you end up doing is you're trying to make your eye as small as possible while the data is still indistinguishable. And if you start going fast and fast, probabilistically, the eye closes, and now you can't distinguish between 1s and 0s. So the answer, every time you ask a question, I answer a different question. That's fine. But the answer to your question is yes, it can become a problem. Then you're actually looking at E&M world for bus structures. And for this class, you don't have to worry about that particular problem. Yeah.
Kind of a follow-up on the pulse thing. So imagine my wave moving like towards the receiver,
Yep.
right? But what's pulling it towards the receiver? Like who's to say I have this 1 and then after this a 0 and then they just like combine? Why does it always go to the right?
Well, say you have something that transmits here.
Yeah.
So in your world, it's a GPIO pin that's going high or low. It's pushing out current or sucking current in. It's setting the voltage high or setting the voltage low. And here you have a high impedance node or something that will accept energy into it. It's not being driven this way. So you need something that drives a signal and something that receives a signal. Again, I didn't answer your question you asked. Does that make sense, or do you have a different question?
Electromagnetics is probably just the answer.
Yes, okay, yeah, E&M. There are E&M classes. I took them way back when I was in your shoes, and I forgot all that stuff. All right, any other questions about buses? These sorts of questions? Basically, this comes back to the rule of thumb that if your distance between here is approximately 1/10 of the wavelength of your thing, then you start getting these weird effects. And you have to start worrying about, do you have standing waves on your transmission lines? We start calling them transmission lines at this point. Is the impedance over here, does this load look like something that would terminate, or do you could actually have signals that hit this node and travel back? There's all these extra effects. So anyway, yeah.
So buses are pretty much like, I guess, like the highway for this CPU where information gets transmitted.
Yeah. Yeah, and we'll talk about topologies where you're trying to send data all over your PCB, just like we sent data from the core all to all different peripherals on the IC. Okay, so good questions. I think the rule of thumb for you guys is have an idea in your head when you should go talk to the analog and RF engineers. That's really what it is, because these problems are horrible, and they're just a devil to solve. And so go find somebody else to solve them for you. And you guys can learn it. It's not like it's impossible. It's just a whole nother set of skills. Okay, so parallel, low speed. I should say high speed. Let's make it say high speed. Okay. That says nothing. All right, high speed, not too wide. Well, you're not going to go infinitely wide. Typically, on a PCB, 8 bits is about as wide as you're going to go for like this class. You will find certain chips that will have parallel interfaces, but typically you're not going to have 32-bit wide. It's just unmanageable for a PCB. Now, if you get up to the motherboard style, yes, you'll get 32-bit wide buses. It's hard to use. And you can get, especially for memory, right, up to 2 gigabits per second. That's when you got to start thinking about these things as timing as RF world. Yeah.
When you mean wide, you mean just like how many bits?
Yeah. Yeah. All right. Other things can tissue. We talked a little bit about this. The length of your wires makes a big difference. Inherently, you don't want to have long wires. I can't imagine a situation where it's advantageous to have long wires. There is some attenuation of signal. Most likely, you're going to get extra noise from the outside world can get in, or your signal can get out. Those are problems, but also you're going to add this extra capacitance. And we'll see, especially when we talk about I²C, adding capacitance really will slow down your bus to the point where you won't be able to recover bits anymore. Everything will just kind of get mushed together or low-pass filtered, and you won't actually be able to figure out ones and zeros as you would expect. Talked about RF interference. Has anybody heard of twisted pair? All right, so you're just telling me that you did. Good, fantastic, I appreciate that. Twisted pair, the idea, and it took me a while to figure out, is that so this is old telephone cables and now Ethernet. They twist 2 wires around each other because it's very hard to get magnetic fields into those wires, in between those wires. If I had 2 wires like this, I make a big loop, and now they're going to, anytime the passing magnetic field comes through it, you're going to induce some voltage on the wire. It's going to corrupt your signal. Twisted pair, you can go draw out the right-hand rule diagram of that. It's actually nearly impossible to get any signal into them. You keep canceling each other out as you twist them around. And so that's a way to protect the outside world from getting your signal out and protect it from outside signals from getting in. If you're trying to do, I don't know, you have some controller over here and some other, I don't know, shooty, gunny, lightsaber thing over here, and you need to send serial across. You can make yourself a twisted pair just with a drill and 2 wires. So we'll talk about that. Anyways, twisted pair is great. One of the hidden little bits of pain that you will learn is that one of the loudest and most corruptive sources on your PCB that's going to corrupt your power supply is actually your communication buses, because you're trying to be pushing out a bunch of current really fast, say a couple megahertz. And where do those current pulses come from, or where do they go? That's essentially you're trying to take a signal wire from high to low or low to high. It takes a little bit of current, not like a huge amount, but a little bit of current. Where does that come from? It comes from your power supply. Well, your power supply is not really great, or your regulator is not really great at removing high frequency noise, and you start seeing this noise propagates all over your chip, everywhere, all over your embedded system design. And that is why you'll see sometimes you'll have an analog portion to your IC. We'll talk about that when we talk about ADCs and DAC. Well, your STM32 actually has separate power pins for analog power and analog ground, because they want to make sure that the analog parts of your chip don't get corrupted by all the switching and signaling noise that comes off your data buses and your power supplies. Yeah, we talked a little bit about this. The types of wires that you have, especially if they're close to each other, will have crosstalk. Imagine you have the right-hand rule where you have a current that's passing this way. It's going to create a magnetic field that curls around. Well, it's going to curl around next to the next wire next to it, and then that right-hand rule is going to cause current to flow on it. So parallel wires that are parallel to each other will induce voltages and currents onto each other. That's an issue that needs to be overcome, and a good reason why serial is better than parallel. Flow control, we'll talk a little bit about this. Typically, if you have multiple devices, you need some way to select them, so essentially p-select, and also you need to decide, the receiver needs to have some way of telling it that it's ready, right? If you're trying to transmit back and forth, you ask a receiver for something, and it's supposed to send back a data, or ask a peripheral for something. It needs some way to say, okay, whose time is it to talk on this bus? So you should look out for those mechanisms. All right, any questions about speed? All the protocols we talk about, you should think about, are they synchronous or asynchronous? So asynchronous uses less wires, which is nice from a routing point of view. But then it makes the responsibility of the receiver to figure out when to sample. When is it supposed to look at a 1 or a 0? So this is a poor eye diagram. Let's make it a little bit simpler. Right? If you're a receiver, when are you supposed to sample? You don't know. You definitely don't want to be sampling here or here. But is even here, like how? Without somebody to tell you what to do, you have to have some arbitration method to figure out when are you supposed to be sampling. There's usually some synchronous overhead for that, but it's pretty common. There's a bunch of serial protocols that require that are asynchronous. Synchronous is usually nicer. It's more clean. It makes sense. It's much more reliable. But you do have this overhead of as extra signal wire, and that you have 2 wires you have to keep track of and make sure that they're not too close to each other. Other things to consider, you're going to have some clock period, you're going to have some delay on the wire itself. I don't think you'll have to actually consider the wire delay, although it's possible. You'll have to figure out that there will be some inherent skew or low passing of your data as it passes through, and that will contribute to your skew and your data skew and your clock skew. You'll have handshaking and flow control, all these other issues that you'll have to consider. Getting close to the last points of things to consider. The number of devices is particularly important, and that's going to affect the flow control and the extra signals you need in your bus structure. So if you're just going from one point to another point, pretty simple. You don't need to have a bunch of signaling. You don't need to have a p-select line or an equivalent for that, because you already know who you're talking to. So this is This is the cheapest, and there doesn't need to be any tri-states or any way to keep data from going to the wrong direction. However, you start thinking about single source and multi-destinations. Now this is the p-select area where you have these multiple targets. And you have to select and tell which one should pay attention. Typically, that's going to need an extra wire or an addressing scheme to figure out which device needs what. And then it becomes unruly, but happens enough times where you're going to have multiple sources and multiple destinations. And now it's not only that you have to have a p-select so that the peripherals know or the targets know when they're supposed to talk. You might have two controllers that want to take control over this bus. Which controller is in charge, or which controller can grab control of the bus without causing collisions, without causing communication bus problems. So this becomes a larger and a harder problem, and so it's good to think about, does the protocol that you're trying to implement actually have a method for handling multiple sources or not? Okay. Arbitration schemes, these are somewhat similar. So arbitration schemes, we'll talk about, is it daisy chains, or so basically this is like the topology and who gets to control this, who's deciding when things talk. So is it that devices are selected? Is there a fixed order sometimes about when devices talk? And it's not unreasonable. Usually most embedded systems will have like 4 or 5 devices maybe that will be on a particular bus, but it's not unreasonable to have things that might have 100 different devices on there, and that's when these issues become more significant. Most LED lights are actually a serial protocol, and so in my lab we have, I think, 15,000 LEDs are all linked up together, and somebody had to figure out the protocol of how we were going to send each individual LED I mean, we didn't come up with that, good gosh, but engineers did figure out how to address and control each individual LED when there's so many of them. So what would be the correct, a good methodology for that? So there's daisy chain token, centralized and decentralized methods. Okay. And these are just protocols that you should be aware of. We'll talk about these 3. So UART, which is the predecessor or the result of RS-232, which came before it. I2C, which is actually a proprietary protocol developed by Philips, but now is the de facto standard. And then SPI, which actually there is no official standard for SPI. It's kind of the Wild West, but everybody uses it. And you will learn the subtle pain of when one company chooses one set of features while the other company doesn't, because nobody demanded that everybody chooses the same number of features. So those are the 3 we'll mostly talk about. Other ones that are important, at least to be aware of and what it would take. So Ethernet, IR data association, whatever this is, basically remote controls, USB, Bluetooth. I should have added on here Zigbee, which you guys will use a lot in your method and your projects. And you might say, well, how is this a serial protocol? But the way in which Bluetooth and Zigbee work is basically just 2 devices talking to each other over serial. It just happens to be the medium's air instead of copper or IR light. All right. So that's the end of the overview of serial protocols versus parallel protocols. Are there any questions before we break?
Does everything wireless have to be serial? Has anyone tried wireless?
Yeah. The latest chipsets are MIMO, so multiple input, multiple output. And what you do is you'll actually be transmitting, like a lot of routers, you'll see 3 antennas. And so those can send multiple data. It just becomes much more complex to receive it and get valuable information out of it. But it totally works. It's just another level of complexity. Yeah.
So these companies that came up with these protocols, like Philips and Motorola, are they still collecting proprietary?
Oh yeah, some of them yes, and some of them no. Actually, it was Ericsson who started developing the Bluetooth spec, got a whole bunch of companies on board, and then told them all, oh, West, right, we have IP in this zone. sorry about that, forgot to tell you. And they started collecting huge royalties off of that and pissed off everybody in the industry. A lot of the other ones like I2C, it's what they do is they make it free for you as developers to buy the chips and put them down, but to register the address that you would need to use I2C, somebody has to agree on the number of addresses for each IC, and so the manufacturers of the chips have to go and pay whatever, as Motorola, whoever this is, some amount of money to manage that. So yeah, all of this is based on somebody making money at some point. All right, any other final questions? All right, I look forward to seeing you all on Friday. That.
Or I can just any of my ideas.
Well, let me see on Thursday, before Friday, look at your slides.
I mean, I'll try to push things tonight.
Hello.
Antoine, I sent you an email about my comparable exams.
Oh, that's right.
So
Yeah,
I'm
it's
sure
fine.
that you received that.
You just like
You know, my apologies. I get back to you.
Oh, it's totally fine.
So right now,
You leave that Thursday?
Yeah.
What time?
3 p.m. I can take it in the morning.
Okay. Can you also do it like Monday after?
Yeah.
Okay.
Or earlier, whatever's most convenient. I don't mind.
Okay, I'll try and get back to you soon so you know what to plan on, but it'll probably be the Monday after.
Okay.
Okay, yeah.
So when are you leaving, traveling?
I'm going to leave Saturday.
Saturday, okay. So is there any way you could open your office hours like Friday or something?
That's office hours on Thursday.
I have
Oh, you
an
can.
exam.
Do you have a question right now I can answer, or do you want to do Friday office hours too?
Yeah, I was gonna like start on the homework a bit after Thursday too. That's why I was asking if you can do Friday.
Okay.
If you're not able to, it's fine. It's not a big deal.
I'll find somebody. I can do it. Send me, well, hold on. Let's do it right now.
I'll just send you an email or something.
No, I'm bad at email. We can do that. Straight up. How about 3:30 on Friday?
Yeah, that works.
Or, yeah, let's do 3:30 on Friday.
2:30.
Yeah.
Okay, that's fine. That works. Thank you.
Have you started coding? A little bit, but I haven't. We worked on it like over the weekend on Saturday, but we never like. I haven't really touched it. How about you?
I set up the repository with like according to the default project. But like other than that,